June 17th, 1943, 27,000 feet above the Belgian coastline. Lieutenant Robert Johnson pushed the control column forward and rolled his P-47C Thunderbolt into a shallow dive. Below him, scattered across the summer sky, 12 Focke-Wulf 196 climbed toward the bomber stream. The German fighters moved with the confidence of predators who had learned to expect easy kills against American escorts. Johnson's wingman called out the contact. The Thunderbolts had altitude, they had position. What they did not have was the respect of the Luftwaffe pilots climbing toward them. For 6 months, German fighter pilots had encountered this massive American fighter and learned its weaknesses. The P-47 was enormous, weighing nearly 13,000 pounds fully loaded, more than twice the weight of a Spitfire. It could not turn. It could not climb with German fighters. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Luftwaffe pilots had taken to calling it der Kanonenboot, the gunboat, a dismissive term that captured both its size and its perceived sluggishness. What the few WWII pilots climbing through 20,000 feet did not know was that they were about to encounter the one-flight regime where the massive Thunderbolt transformed from liability into lethal advantage. Johnson selected his target and pushed the throttle to war emergency power. The massive Pratt and Whitney R-2800 radial engine, all 2,000 horsepower of it, pulled the nose toward vertical. The Thunderbolt accelerated. At 25,000 feet, the airspeed indicator swept past 400 miles per hour. At 22,000 feet, it reached 450. The controls grew heavy, requiring increasing force to maintain the dive angle. The German fighters scattered. One F-01-90 pilot saw the diving American and did what had worked for months. He pulled into a steep climb. In a Spitfire or a Messerschmitt 109, this maneuver would have left the pursuing fighter wallowing, bleeding energy, unable to follow. But Johnson's Thunderbolt was not a Spitfire. 7 tons of American engineering had accumulated velocity that could not be bled away simply by pulling up. Johnson followed. The German pilot climbed steeper, expecting the American to fall away. Instead, Johnson's gun sight remained locked on the few FA-190's fuselage. At 480 miles per hour, Johnson opened fire. 8 50 caliber machine guns, synchronized to converge at 300 yards, poured 200 rounds per second into the air. The W-190 staggered as dozens of armor-piercing incendiary rounds tore through its engine cowling and wing root. Black smoke erupted from the fighter as it rolled inverted and fell toward the channel. Johnson pulled out of the dive at 15,000 feet. The controls were almost immovable, requiring both hands and considerable force to begin recovering to level flight. But he recovered. The Thunderbolt's massive wing area and sturdy construction absorbed forces that would have torn lighter aircraft apart. As Johnson climbed back toward the bomber stream, his radio crackled with reports from other pilots in his squadron. 3 more FW-190s destroyed, all in diving attacks where German pilots had attempted to escape by climbing, only to discover that the massive American fighter could follow them through maneuvers that should have been impossible. The German pilots who survived that engagement returned to their bases shaken. They had encountered something that contradicted everything they knew about fighter combat. Heavy aircraft did not accelerate in dives. Heavy aircraft did not maintain control at extreme speeds. Yet the American Thunderbolt had done both, turning what should have been an easy victory into a one-sided slaughter. This was not how the story was supposed to unfold. When the Republic P-47 Thunderbolt first arrived in England in December 1942, American pilots greeted it with dismay, bordering on anger. Pilots from the 4th Fighter Group, who had previously flown Spitfires with the Royal Air Force, looked at the massive fighter with undisguised horror. The Thunderbolt dwarfed every fighter they had seen. It was enormous. British pilots joked that a Thunderbolt pilot could defend himself from a Luftwaffe fighter by running around inside the fuselage and hiding. The nickname Jug originated from this first impression. The aircraft's profile resembled a common milk jug, with its bulbous fuselage housing the massive radial engine and turbo supercharger system that gave it high-altitude performance. Some American pilots called it even less flattering names. 7-ton milk bottle, cast iron beast, repulsive scatterbolt. Dom Blakesley, commanding officer of the 4th Fighter Group's 335th Fighter Squadron, examined his new mount with barely concealed contempt. When Republic representatives assured him the Thunderbolt's diving performance was exceptional, Blakesley replied, "It ought to be able to dive. It certainly can't climb." His assessment was not wrong. Early model P-47Cs equipped with narrow-blade propellers climbed poorly. German fighters could easily climb away from pursuing Thunderbolts. At low and medium altitudes, where most combat occurred, the P-47 was demonstrably inferior to both the 4-190 and the Messerschmitt 109 in maneuverability and climb rate. But dismissing the Thunderbolt based on these deficiencies ignored the physics that made it extraordinary in one critical flight regime. Physics that German fighter pilots would learn about in the hardest possible way. The story of how the P-47 came to dominate one aspect of aerial warfare begins with fundamental principles of motion and energy. Every aircraft, when pointed nose down and allowed to accelerate, reaches a point where drag forces exactly equal the combined forces of gravity and thrust. At this equilibrium, the aircraft stops accelerating. This maximum speed in a vertical dive is terminal velocity, the fastest an aircraft can fall regardless of how much power the engine provides or how steep the dive angle. For most World War II fighters, terminal velocity was limited not by engine power but by structural strength and control surface effectiveness. As aircraft approached 400 to 450 miles per hour in steep dives, several phenomena occurred simultaneously. Air flowing over the wings and control surfaces began approaching the speed of sound, creating shock waves that dramatically altered lift and control effectiveness. This was compressibility, and it killed pilots who did not understand it. The Messerschmitt 109, backbone of the Luftwaffe fighter force, encountered severe compressibility problems above 400 miles per hour. As airspeed increased, the elevator control became progressively heavier. At 400 miles per hour indicated airspeed, the elevator required significant force to move. Above 450 miles per hour, it became almost immovable. Multiple Messerschmitt pilots died attempting to dive away from pursuing Allied fighters, only to discover they could not pull out of the dive before hitting the ground. The elevator, locked by aerodynamic forces approaching transonic speeds, refused to generate enough force to overcome the aircraft's inertia. The Focke-Wulf 190 fared somewhat better. Its radial engine and more robust construction allowed it to reach higher speeds before encountering compressibility. But even the FAR 190 had limits. Above 420 miles per hour, elevator forces became excessive. Pilots attempting to pull out of dives at these speeds required both hands on the control column and considerable upper body strength. More importantly, both German fighters were light. The Messerschmitt 109G weighed approximately 6,400 pounds combat loaded. The FAR 190A weighed around 8,500 pounds. Their relatively low weight meant they reached terminal velocity at speeds where their control surfaces still functioned adequately. A diving Messerschmitt 109 might reach 450 miles per hour before aerodynamic forces balanced its weight. A Teblo 190 could reach perhaps 480 miles per hour under optimal conditions. The P-47 Thunderbolt weighed 13,000 pounds when fully loaded for combat. It was nearly twice as heavy as a Messerschmitt and significantly heavier than any other single-engine fighter in operational service. This enormous mass, combined with its relatively large wing area and powerful engine, created diving characteristics unlike anything German pilots had encountered. When pointed straight down from 30,000 feet with the throttle at maximum power, a P-47 accelerated with inexorable force. The massive weight generated gravitational force far exceeding what lighter fighters could produce. The 2,000 horsepower R-2800 engine added thrust that lighter fighters could not match. As the aircraft descended into denser air at lower altitudes, where its engine produced maximum power, acceleration increased further. Alexander Kartveli, the Republic aviation engineer who designed the P-47, had created the aircraft around a specific set of requirements. The Army Air Forces wanted a fighter capable of operating at altitudes above 30,000 feet, where the thin air reduced the effectiveness of naturally aspirated engines. To achieve this, Kartveli selected the Pratt and Whitney R-2800 double wasp, an 18-cylinder radial engine producing 2,000 horsepower at sea level. To maintain power at altitude, he added a turbo supercharger mounted in the rear fuselage. The turbo supercharger system required ducting that ran from the engine cowling along the fuselage sides to the turbine in the tail section, then back forward to the engine intake. This complex plumbing added weight and volume. The engine itself weighed considerably more than the inline engines used in most contemporary fighters. The massive four-bladed propeller, 12 feet in diameter, added more weight. Armor plating, protecting the pilot, and critical systems added still more weight. 8 50 caliber machine guns, mounted 4 per wing, with 400 rounds per gun, represented a weapons load exceeding that of any other American fighter. When engineers totaled the weight, they discovered they had created a fighter that violated conventional wisdom. Traditional fighter design emphasized minimal weight to maximize climb rate and maneuverability. The P-47 was heavy where other fighters were light, large where other fighters were compact. Early test flights confirmed what skeptics feared. The P-47 climbed slowly compared to German fighters. At low and medium altitudes, it could not match the turn rate of Spitfires or Messerschmitts. But during those same test flights, pilots discovered something remarkable. When pointed downward from altitude, the Thunderbolt accelerated like no other aircraft they had flown. During one test flight in November 1942, Lieutenant Harold Comstock and Roger Dyer conducted performance testing at 30,000 feet. After completing a level speed run, they pushed the nose over to descend to the next test altitude. Within seconds, their airspeed indicators showed velocities approaching 500 miles per hour. The aircraft began buffeting violently as it approached compressibility. Both pilots managed to recover, but the experience was terrifying. Later analysis revealed their indicated airspeeds had been exaggerated by pitot-static system errors at high speeds. The actual velocity was probably closer to 550 miles per hour, true airspeed at altitude, or approximately 0.81 Mach. This was approaching the speed of sound, far beyond what any other piston-engine fighter could achieve safely. Republic engineers recognized they had created an aircraft with extraordinary diving characteristics. More importantly, they realized the controls remained effective at speeds where lighter fighters became uncontrollable. The P-47's large control surfaces, actuated by rigid push rods rather than cables, maintained effectiveness even as airspeed increased dramatically. The massive airframe, built to withstand the structural loads imposed by operating at extreme altitudes, could absorb the forces generated during high-speed dives. The challenge became convincing pilots to exploit this advantage. American pilots arriving in England throughout early 1943 brought tactical doctrines developed through training and refined through combat experience. These doctrines emphasized achieving position advantage through climbing and turning. Speed was valuable, but most pilots understood speed primarily as a means to gain altitude or to disengage from unfavorable combat. Few pilots understood how to use diving performance offensively. The concept required thinking about aerial combat in terms of energy rather than position. An aircraft at high altitude possessed potential energy. When that aircraft dived, potential energy converted to kinetic energy speed. The heavier the aircraft, the more potential energy it possessed at any given altitude. The more powerful the engine, the more additional kinetic energy could be added during the dive. Lieutenant Colonel Hubert Zemke, commanding the 56th Fighter Group based at Halesworth in Suffolk, understood this principle. Zemke had studied physics and engineering before entering military service. He recognized that his massive Thunderbolts, despite their poor climbing performance, possessed an advantage that could be exploited through proper tactics. Throughout January and February 1943, Zemke developed what would become known as the Zemke Fan, a formation and tactical doctrine specifically designed around the Thunderbolt's strengths. Rather than attempting to engage German fighters in turning dogfights where the P-47 was at a disadvantage, Zemke trained his pilots to maintain altitude advantage, identify targets below them, dive at maximum velocity, make a single high-speed firing pass, then use the energy from the dive to zoom climb back to altitude. The tactic worked brilliantly when executed properly. German fighters that attempted to evade by diving discovered the pursuing Thunderbolts could match or exceed their diving speed. German fighters that attempted to evade by climbing discovered the diving Thunderbolts retained so much energy that they could follow through climbing maneuvers that should have been impossible. The transformation became undeniable during Big Week, the massive Allied bombing campaign against German aircraft production facilities in late February 1944. Between February 20th and 25th, the 8th Air Force launched over 3,800 bomber sorties deep into Germany. The Luftwaffe responded with everything available, throwing over 2,000 fighter sorties against the incoming bomber streams. German fighter controllers expected another brutal series of engagements where their experienced pilots would inflict painful losses on American bombers and their escorts. What they encountered instead was a transformed American fighter force that had learned to fight to the strengths of their massive Thunderbolts. On February 22, 1944, Oberleutnant Wilhelm Hoffmann led his starful of Focke-Wulf toward a formation of B-17 seconds approaching Leipzig. Hoffmann was an experienced pilot with 16 victories, most achieved on the Eastern Front before his transfer west to face the American daylight bombing campaign. He had fought Thunderbolts before and knew their weaknesses. Stay away from them at high altitude, where their turbo-supercharged engines gave them power advantages. Engage at medium altitudes, where their poor climb rate made them vulnerable. Most importantly, never try to outdive them. The American fighters were too fast in dives, but Hoffmann's starful needed to attack the bombers, and that meant accepting engagement with the escorts. As his formation approached the bomber stream at 24,000 feet, Hoffmann spotted a flight of 4 Thunderbolts positioned 3,000 feet above and slightly ahead of the bombers. Perfect escort position, but too far away to prevent a quick slashing attack if executed properly. Hoffmann led his fighters into position, timing the approach to coincide with a gap in the fighter coverage. At 600 yards from the bombers, he selected his target, a B-17 flying in the low element of the formation. His finger tightened on the trigger as he prepared to fire. Then his wingman's voice crackled urgently over the radio. "Achtung! Behind us! Diving fast!" Hoffmann glanced back and felt ice flood his stomach. 2 Thunderbolts were diving nearly vertically, already past 500 miles per hour and accelerating. They had seen Hoffmann's starful positioning for the attack and had rolled into near-vertical dives to intercept. The range closed with terrifying speed. Hoffmann broke left and pulled into a climbing turn. This was the standard evasion against diving attackers. Bleed their speed by forcing them to climb. Make them choose between maintaining pursuit or maintaining energy. The Thunderbolt could not do both. Except this time, it did both. The lead American pilot, Major Francis Gabreski of the 56th Fighter Group, had executed this maneuver dozens of times. He understood exactly how much energy his diving Thunderbolt possessed and how much he could spend pursuing a climbing target. As Hoffmann pulled up, Gabreski followed, maintaining his dive angle until the last possible moment, then pulling smoothly into a climbing pursuit curve. The Thunderbolt's massive weight carried it through the maneuver with momentum that lighter fighters could not match. At 17,000 feet, with his WWII standing nearly vertical, Hoffmann looked back again. The Thunderbolt was still there, perhaps 400 yards behind, its nose tracking steadily. Gabreski's gun sight centered on the Focke-Wulf's fuselage. He pressed the trigger. 8 .50 caliber guns hammered in unison. The first burst went high. Gabreski adjusted slightly, compensating for the vertical angle and the closure rate. The second burst found its mark. Armor-piercing incendiary rounds tore through the Focke-Wulf's engine cowling. The BMW 801 radial engine shattered as rounds severed fuel lines and ignited atomized gasoline. Hoffmann had perhaps 2 seconds to realize what was happening before the fire reached the main fuel tank behind the engine. The Focke-Wulf exploded, the overpressure from the fuel detonation tearing the fighter's fuselage in half. Hoffmann's parachute deployed moments before the wreckage tumbled past Gabreski's Thunderbolt. Gabreski pulled out of his climb at 19,000 feet, having lost only 5,000 feet of altitude despite following the Focke-Wulf through a climbing evasion that covered nearly 8,000 feet of vertical distance. The energy from his initial dive at 27,000 feet had carried him through the entire engagement without ever entering a flight regime where his Thunderbolt was disadvantaged. This engagement, repeated across dozens of similar encounters during Big Week, revealed the fundamental transformation in the air war over Europe. German fighter pilots could no longer rely on climbing away from pursuing American fighters. The massive Thunderbolts, when properly positioned at altitude, possessed diving energy that could not be bled away through conventional evasion maneuvers. The psychological impact was immediate and severe. Luftwaffe pilots who had grown confident engaging American escorts suddenly faced tactical situations where their training and experience provided no advantage. A diving Thunderbolt could not be evaded by climbing. It could not be outrun in level flight after it converted dive energy into forward speed. German pilots attempting to dogfight with Thunderbolts that still possessed energy found themselves facing aircraft that, while still inferior in turn rate, could use vertical maneuvers to maintain initiative. By March 1944, Luftwaffe intelligence officers were collecting disturbing combat reports from surviving pilots. The reports described American Thunderbolts achieving speeds in dives that seemed impossible. Claims of American fighters diving at 550 miles per hour were dismissed as exaggeration born from combat stress. German intelligence knew the Mustang's maximum dive speed was approximately 505 miles per hour indicated airspeed. The Thunderbolt, being heavier and less streamlined, should have been slower. Yet pilots continued reporting encounters with Thunderbolts that seemed impossibly fast in dives. What German intelligence failed to understand was that the Thunderbolt's weight was not a liability in dives, but rather a decisive advantage. The physics were straightforward but counterintuitive. In a vertical dive, gravitational force accelerates an object at 32 feet per second squared, regardless of mass. But aerodynamic drag opposes this acceleration, and drag increases with the square of velocity. For a light aircraft like the Messerschmitt 109, drag forces balanced gravitational forces at relatively low speeds. The aircraft simply did not have enough mass to overcome the air resistance at higher velocities. For the massive Thunderbolt, drag forces did not balance gravitational forces until much higher speeds. The aircraft's weight allowed it to punch through air resistance that stopped lighter fighters. Additionally, the Thunderbolt's wing loading the ratio of weight to wing area worked in its favor during dives. The P-47 had a wing loading of approximately 35 pounds per square foot. This was lower than might be expected for such a heavy aircraft because Republic engineers had given it relatively large wings to maintain controllability at the high altitudes where it was designed to operate. During dives, this wing loading meant the aircraft generated less lift for its weight compared to fighters with lower wing loading. Less lift meant less vertical force opposing the dive, which translated to faster acceleration. The Thunderbolt quite literally fell faster than lighter fighters because its wings did not slow its descent as effectively. The engine contributed additional advantage. The Pratt and Whitney R-2800, with its turbo-supercharger system, maintained maximum power output down to approximately 27,000 feet. Even in a vertical dive, the engine could provide up to 2,000 horsepower of thrust, further accelerating the aircraft beyond what gravity alone could achieve. German fighters, with their naturally aspirated or mechanically supercharged engines, lost power as they descended from altitude, producing maximum output only at their rated altitude. Combat reports from spring 1944 demonstrate how thoroughly Thunderbolt pilots had learned to exploit these advantages. On April 5, 1944, Captain Walker Mahurin of the 56th Fighter Group encountered a formation of Messerschmitt 109s attacking B-17 seconds near Brunswick. Mahurin was positioned at 29,000 feet, approximately 5,000 feet above the German fighters. He rolled inverted and pulled through into a near-vertical dive, accelerating past 500 miles per hour indicated airspeed. The Messerschmitt he selected as his target saw the diving American and attempted the standard evasion. He pushed over into a dive, attempting to use his lighter fighter's superior diving acceleration to escape. But the physics of the situation doomed this tactic from the start. The Messerschmitt accelerated quickly to approximately 450 miles per hour, then began encountering compressibility effects. The elevator stiffened. Control effectiveness deteriorated. The German pilot had two choices: pull out of the dive while he still had control authority, or continue diving and risk losing the ability to recover before impact. He chose to pull out. As he did, Mahurin's Thunderbolt closed the range from 600 yards to 300 yards in less than 3 seconds. At that range, with a 50-mile-per-hour closure rate, Mahurin could not miss. His guns hammered for 2 seconds. The Messerschmitt staggered as rounds tore through the cockpit and engine. The fighter rolled inverted and entered an uncontrolled spin. Mahurin did not see a parachute. The numbers told the story. During first quarter 1944, before Thunderbolt pilots fully mastered dive and zoom tactics, American fighters in Europe achieved an overall kill ratio of approximately 1.8 to 1 against German fighters. By second quarter 1944, with dive tactics becoming standard doctrine, the kill ratio improved to 3.2 to 1. This improvement occurred even as German fighter production increased and Luftwaffe units fielded more aircraft. The difference was not in aircraft numbers but in tactical employment. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. German pilots who survived encounters with diving Thunderbolts returned to their bases with consistent accounts. The American fighter was impossibly fast in dives. It could follow German fighters through evasive maneuvers that should have caused it to lose position. Most disturbingly, the Thunderbolt's pilots seemed to understand these advantages and deliberately positioned themselves to exploit them. Kurt Bühligen, a Luftwaffe ace with 112 victories, encountered Thunderbolts repeatedly during 1944. In post-war interviews, he described the tactical dilemma German pilots faced. The P-47 was very heavy, too heavy for some maneuvers. We would see it coming from behind and pull up fast, and the P-47 couldn't follow, and we came around and got on its tail in this way. This statement, accurate for engagements at medium altitudes where both aircraft began at similar speeds, did not apply to engagements where the Thunderbolt initiated combat from altitude with a diving attack. Bühligen's second statement revealed the adaptation German pilots were forced to make, but we learned not to try to dive away from them. They were faster than anything in a dive. By summer 1944, Luftwaffe tactical doctrine explicitly warned against diving away from pursuing Thunderbolts. The guidance recommended climbing away from P-47 seconds, attempting to exploit their poor climb rate to break contact. But this tactic only worked if the German pilot could initiate the climb before the Thunderbolt entered firing range. Against a diving Thunderbolt with energy advantage, climbing away was futile. The transformation extended beyond simple dive speed. Thunderbolt pilots learned to manage energy in ways that multiplied their tactical advantages. After making a high-speed diving attack, the pilot would use the momentum from the dive to zoom climb back to altitude, trading speed for height. This maneuver, executed properly, could return the Thunderbolt to 25,000 or 26,000 feet, even after diving to 15,000 feet to make an attack. The physics were elegant. A Thunderbolt, diving from 27,000 feet to 15,000 feet, lost 12,000 feet of altitude, but gained approximately 200 miles per hour of airspeed. If the pilot then pulled into a zoom climb at 500 miles per hour, the aircraft could climb back to 24,000 or 25,000 feet before speed bled off to the point where climb rate became unsustainable. The pilot had traded 2,000 to 3,000 feet of altitude for a firing pass that might have destroyed an enemy fighter. German pilots attempting to counter this tactic found themselves in impossible situations. If they pursued the zooming Thunderbolt, their lighter fighters reached stall speed long before catching the American. If they broke away to attack the bombers, they exposed themselves to another diving attack from Thunderbolts that had regained altitude advantage. Adolf Galland, General der Jagdflieger and one of Germany's most experienced fighter leaders, flew a captured P-47 inches late 1943 to understand its capabilities. After the flight, he reported to Reichsmarschall Hermann Göring that the Thunderbolt represented a formidable opponent despite its size and weight. Galland noted the aircraft's exceptional diving performance and the tactical flexibility this provided to American pilots. More importantly, Galland recognized that German fighters lacked effective counters to properly executed dive and zoom tactics. The Focke-Wulf 190, with its superior roll rate and better diving characteristics than the Messerschmitt 109, could at least attempt to follow a diving Thunderbolt for short periods. But even the Focke-Wulf 190 could not match the American fighter's combination of diving acceleration, high-speed control authority, and structural strength. The structural advantage deserves emphasis. Aircraft diving at extreme speeds experience aerodynamic loads that increase exponentially with velocity. Wings flex under these loads. Control surfaces generate forces that can tear mounting brackets from airframes. Fuselages twist as asymmetric forces act on different sections. Republic Aviation had built the P-47 around a design philosophy emphasizing strength over lightness. The wing spars were massive forgings of aluminum alloy, far stronger than necessary for normal flight operations. The fuselage frame consisted of heavy bulkheads and stringers that added weight, but provided immense strength. Control surfaces were mounted on reinforced attachment points, designed to handle loads far exceeding normal operational requirements. This overbuilt construction allowed the Thunderbolt to dive at speeds that would have caused structural failure in lighter fighters. On multiple occasions, P-47 pilots returned from missions with fabric covering torn from control surfaces or wings, showing permanent deformation from high-speed maneuvers. Yet the aircraft remained flyable, testament to the strength Republic engineers had built into the design. The ultimate demonstration of the Thunderbolt's diving supremacy came not in a single dramatic engagement, but through the accumulated weight of hundreds of encounters where physics proved decisive. By June 1944, as Allied forces prepared for the invasion of Normandy, the tactical air war over Western Europe had fundamentally shifted. German fighter pilots no longer attacked bomber formations with the aggressive confidence that had characterized their operations in 1943. Instead, they approached with caution, constantly scanning the sky above for diving Thunderbolts. The psychological transformation was complete. The aircraft German pilots had mocked as Der Kanonenboot slow, ungainly, unsuited for fighter combat, had become the weapon they feared most when it appeared above them with altitude advantage. On June 6, 1944, as Allied troops stormed the beaches of Normandy, Thunderbolts provided continuous air cover throughout the day. German fighters that attempted to interfere with the invasion fleet were consistently intercepted and destroyed. The Luftwaffe managed fewer than 100 sorties over the invasion beaches during the critical first 24 hours. American fighters flew more than 8,700 sorties during the same period. This overwhelming air superiority was possible because American fighter tactics had evolved to exploit the Thunderbolt's strengths while minimizing its weaknesses. The massive fighter that could not climb with German opponents, that could not turn with Spitfires or Messerschmitts, had found its role as the ultimate diving interceptor. Positioned at altitude, Thunderbolts controlled the airspace beneath them absolutely. No German fighter could escape a diving P-47 with energy advantage. No German fighter could survive in an engagement where the American pilot maintained initiative through vertical maneuvers. The engineering that made this dominance possible remained invisible to most observers. What pilots experienced as the jug dives like a rock was actually a complex interaction of mass, wing loading, engine power, control surface design, and structural strength. Each element contributed to performance that exceeded what German engineers had thought possible for an aircraft of such massive proportions. Consider the propeller. The four-bladed Curtiss electric propeller fitted to most P-47 seconds had a diameter of 12 feet and weighed approximately 450 pounds. This massive propeller generated tremendous thrust, even at high airspeeds, where smaller propellers would have been inefficient. During dives, when the aircraft accelerated past 450 miles per hour, the propeller continued producing forward thrust rather than simply windmilling. This added perhaps 500 horsepower of effective thrust to the gravitational forces accelerating the aircraft downward. Consider the cooling system. German fighters with inline engines struggled with cooling during prolonged high-speed flight. The Messerschmitt 109's coolant radiators, mounted under the wings and fuselage, created drag that limited maximum speed. More critically, during extended combat at high power settings, these engines risked overheating. The P-47's radial engine, air-cooled by a fan driven directly from the crankshaft, had no such limitations. The massive cowling opening at the front of the fuselage captured enormous amounts of cooling air at high speeds. The faster the aircraft flew, the more cooling air reached the engine. Pilots could hold maximum power settings during prolonged dives without risking engine damage. This meant Thunderbolt pilots could use full throttle throughout a dive, adding engine thrust to gravitational acceleration for the entire descent. Consider the turbo supercharger. Most fighters used mechanically driven superchargers that consumed engine power to compress intake air. The P-47's turbo supercharger was driven by exhaust gases that would otherwise have been wasted. This meant the full 2,000 horsepower of the R-2800 engine was available for thrust, with no power diverted to drive auxiliary systems. During dives from high altitude, this gave the Thunderbolt a power advantage over German fighters, whose mechanical superchargers consumed up to 200 horsepower. The cumulative effect of these engineering choices created performance that seemed almost magical to pilots who learned to exploit it. Robert S. Johnson, who scored 27 victories flying Thunderbolts with the 56th Fighter Group, described the experience in post-war interviews. "When you rolled that jug over and pointed her downhill, you had a feeling of absolute power. Nothing could stay with you. Nothing could escape. You could take that dive all the way down from 30,000 feet to the deck and still have control. The Germans knew it. You could see them look up, see you diving on them, and just give up. They knew they couldn't get away." Johnson's most famous combat, on June 26, 1943, illustrated both the Thunderbolt's strengths and its limitations. Separated from his formation and damaged by multiple cannon hits from Focke-Wulf W190s, Johnson attempted to escape by diving for the deck. His Thunderbolt, even severely damaged, accelerated away from the pursuing German fighters. At 500 miles per hour, with hydraulics shot out and half his controls damaged, Johnson still maintained enough control authority to keep the aircraft flying. One German pilot pulled alongside the damaged Thunderbolt, apparently examining the battle damage. Then, rather than delivering the killing shots, the German pilot saluted and broke away. Johnson nursed his battered fighter back to England, the massive airframe absorbing damage that would have destroyed lighter aircraft. He counted over 200 bullet and cannon shell strikes on his aircraft after landing. Yet, it had remained flyable throughout, testament to both structural strength and sheer mass. By autumn 1944, the diving tactics pioneered by Zemke, Gabreski, and other Thunderbolt pilots had become standard doctrine across all American fighter groups in Europe. Training emphasized maintaining altitude advantage, identifying targets below, executing vertical diving attacks, and using zoom climbs to regain position. The tactics worked so consistently that kill ratios continued improving even as German fighter production increased and the Luftwaffe deployed more aircraft. Between April and September 1944, Thunderbolts were credited with destroying over 2,000 German aircraft in aerial combat, while losing approximately 400 P-47 seconds to all causes in the European theatre. This 5-to-1 kill ratio represented the peak of Thunderbolt effectiveness. The ratio was achieved not through superiority in all flight regimes, but through ruthless exploitation of the one regime where the P-47 was absolutely dominant, the vertical dive from altitude. German attempts to counter this tactical dominance proved futile. The W190D, introduced in late 1944, featured a liquid-cooled inline engine that provided better high-altitude performance than earlier radial-engined variants. The Dora 9, as pilots called it, could climb faster and had better acceleration than the FW190A. But even the improved FW190D could not outdive a P-47. The physics remained unchanged. The Thunderbolt was still heavier, still more powerful in dives, still capable of higher speeds with better control authority. The tactical implications extended beyond air-to-air combat. Thunderbolts conducting ground attack missions could dive on targets at speeds exceeding 500 miles per hour, deliver bombs or rockets with accuracy enabled by the aircraft's stability at high speeds, then climb away before ground-based anti-aircraft gunners could track the target. The same diving performance that made the P-47 lethal against German fighters made it equally deadly against ground targets. By February 1945, organized Luftwaffe resistance over Western Europe had effectively ceased. German fighter units were being withdrawn to defend the homeland against the strategic bombing campaign. Thunderbolts ranged across Germany with near impunity, destroying aircraft on the ground, attacking transportation networks, and maintaining air superiority that made Allied ground operations possible. The final accounting reveals the Thunderbolts' contribution to Allied victory. Between January 1943 and May 1945, P-47 seconds were credited with destroying approximately 3,752 German aircraft in aerial combat, while losing 824 Thunderbolts to enemy fighters. This overall kill ratio of 4.6 to 1 ranked among the best achieved by any fighter type during the war. More importantly, the Thunderbolt achieved this ratio while conducting missions deep into German-held territory, where Luftwaffe fighters had every advantage of operating over their own bases with short distances to friendly airfields. The aircraft German pilots had initially dismissed as too heavy, too large, too ungainly for serious fighter combat, had proven decisively effective through one fundamental advantage. It could dive faster than anything in the sky and retain control authority at speeds where other fighters became uncontrollable. The physics that made this possible were not revolutionary. Engineers had understood for decades that heavier objects accelerate to higher terminal velocities in free fall. What Republic Aviation accomplished was building an aircraft strong enough to withstand the structural loads of diving at speeds approaching the sound barrier, with controls that remained effective at those speeds, and with engine power that enhanced rather than limited diving performance. German engineers understood these principles as thoroughly as their American counterparts. But German industry in 1943 and 1944 could not support development of new fighter designs optimized for the high-speed diving combat that Thunderbolt tactics had made dominant. German factories operated at maximum capacity, producing existing designs in quantities barely sufficient to replace combat losses. Introducing radical new designs would have required retooling production lines and accepting months of reduced output. Germany could not afford this disruption. This highlighted a fundamental asymmetry in the air war. American industry could identify tactical deficiencies, develop engineering solutions, and implement those solutions at scale while maintaining production of existing types. German industry could barely maintain existing production levels against mounting Allied bombing pressure and resource shortages. The paddle blade propeller modification that transformed Thunderbolt climb performance, the development of 150-grade fuel that increased engine power. These represented incremental improvements that American industry could implement rapidly. German industry lacked the capacity for such responsive adaptation. The story of the Thunderbolt's diving supremacy is ultimately a story about industrial capacity expressed as physical advantage in combat. The massive fighter was heavy because American industry could afford to build heavy fighters and ship them across the Atlantic in quantities that made weight less important than capability. The Thunderbolt had an oversized engine because American petroleum refineries produced unlimited high-octane fuel. The aircraft featured robust construction because American factories could produce vast quantities of aluminum alloy and employ skilled workers to form it into airframes that prioritized strength over minimal weight. German fighters were light because German industry needed to maximize the number of fighters produced from limited aluminum stocks. They featured smaller engines because German synthetic fuel production could not supply unlimited quantities of high-octane gasoline. They were built to minimum structural standards because every kilogram of weight saved meant another fighter could be built from available materials. These industrial realities translated directly into combat performance. In the one-flight regime where weight was advantage rather than liability, the vertical dive from altitude, the Thunderbolt dominated absolutely. German pilots who survived the war consistently cited the P-47's diving performance as its most dangerous characteristic. Heinz Baer, who flew against Allied fighters throughout the war, stated that Thunderbolts had to be handled very carefully and that German pilots learned to avoid diving combat with them at all costs. The broader lesson transcends the specific case of the Thunderbolt versus German fighters. Military effectiveness results from the complex interaction of industrial capacity, tactical doctrine, training, and engineering. The P-47 was not superior to German fighters in most measurable performance categories. It climbed more slowly than the 4-190D. It turned more slowly than both the Messerschmitt 109 and 4-190. Its maximum level speed was comparable to, but not clearly better than, German fighters. But in the one category that mattered most for the escort mission, American fighters were assigned to fly the ability to dive from altitude and destroy or drive away German fighters attempting to attack bomber formations. The Thunderbolt was unmatched. American tactical doctrine evolved to exploit this advantage ruthlessly. Thunderbolts positioned themselves at altitude above bomber streams and waited for German fighters to attack from below. When attacks developed, the P-47 seconds rolled inverted and dove, accelerating to speeds German fighters could not match and could not escape. By May 1945, when Germany surrendered, the Thunderbolt had flown more than 546,000 combat sorties, destroyed more than 11,000 enemy aircraft on the ground and in the air, and established itself as one of the most effective fighter bombers of the war. These achievements rested fundamentally on physics, the physics of mass, velocity, energy, and control, and on engineering that created an aircraft capable of translating physical principles into tactical advantage. The 7-ton milk bottle, the cast-iron beast, the ungainly jug that early pilots had viewed with dismay, had proven that weight was not always a liability. In the sky over Europe between 1943 and 1945, when American pilots pushed their control columns forward and felt their massive Thunderbolts accelerate toward terminal velocity, weight became the decisive weapon. German pilots learned this lesson in the hardest possible way, discovering too late that the lumbering American fighter they had mocked could transform into a 550-mile-per-hour predator that nothing in the Luftwaffe's inventory could escape. The final irony was that the advantage came not from revolutionary technology, but from fundamental physics applied at industrial scale. The Thunderbolt dove faster than German fighters for the same reason a bowling ball falls faster through air than a tennis ball mass overcomes drag. Republic aviation engineers had simply built a fighter heavy enough and strong enough to exploit this principle in combat. The result was an aircraft that dominated one of the most critical aspects of the air war over Europe, proving that sometimes the heaviest fighter wins not despite its weight, but precisely because of it. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.